Hello, my name is Emmanuel Dapaah, and today I'm presenting on the topic an AI-based transmission power control certificate omission in vehicular ad hoc networks. So for the presentation background, we'll first take a look at some background knowledge. Then we also discuss some related works. Then we delve into our proposed congestion control scheme, which is divided into a congestion detection mechanism and a congestion control mechanism. Then we look at the contribution of our work. Then we discuss the simulation setup alongside with the results that were generated. Then we conclude and also show the references. So when we talk of vehicular ad hoc network, this is a communication network that allows vehicles to communicate among themselves by transmitting out periodic beacons. And these periodic beacons allow the vehicles to be aware of their environment, and in so doing are able to take safety critical decisions in time. But as vehicles engage in this kind of communication, this raises the issue of security, that is authentication. How we can authenticate the sender of a message, and not only that, how to also authenticate the integrity of the message that is transmitted by this sender. And we need to do this because some of these messages that are broadcast are messages that contain safety critical information. So to perform this kind of security, researchers have proposed in literature what is termed as a digital certificate. And this is a certificate that is issued by a trusted certificate authority. So with this certificate, it's expected that each vehicle participating in the communication would attach a certificate to the beacon it sends out, so that with this certificate, a receiving vehicle can then authenticate the identity of the sender, as well as be able to verify the integrity of the message it received as well. But as vehicles make use of this kind of security mechanism, it then raises the issue of channel congestion. This is because in literature, the certificate is known to increase the payload size by over 200 bytes. So in situations where vehicle density is very high, this easily causes the communication channel to get congested, and so doing packets getting dropped. So to solve this issue, researchers have proposed in literature a certificate omission scheme. So how this scheme works is that it's expected that, for example, between this red and black vehicle, in their communication, the initial communication, the red vehicle will attach a certificate and then broadcast it with the expectation that the receiving vehicle, which is the black vehicle, will catch the certificate into memory so that in subsequent communication it can omit it. Another example is with this violet vehicle, and also with the ambulance. In the initial conversation, a certificate is attached so that in subsequent it can omit it. So this is the general or basic concept of a certificate omission strategy. But every scheme has its own challenges. The certificate omission strategy is faced with the challenge of how to reduce the number of cryptographic packet loss and how to also reduce the number of network packet loss incurred. Where cryptographic packet loss are the packets that are lost as a result of a receiving vehicle not having a corresponding certificate with which it can verify the beacon it has received. And also a network packet loss being the packets that are dropped over the communication channel as a result of packet collision over the channel. So to address these schemes, researchers have proposed various strategies in terms of certificate omission. First of which is the periodic omission of certificates, where vehicles attach a certificate only on periodic basis, and this scheme is known to reduce the overall communication overhead. But when you analyze its performance, it is noticed to be context dependent. The neighbor-based certificate omission strategy also operates whereby vehicle attaching a certificate only when a new vehicle is identified within its communication range and omitted otherwise. And this scheme also helps to reduce the number of cryptographic packet loss incurred when vehicle density is noticed to be high, but it has a negative impact on the number of network packet loss incurred. Congestion-based certificate omission strategy is a strategy with which vehicles estimate their communication channel load, and if the channel is observed to be free, then no certificate is omitted from the beacons that are sent out. But if the channel is estimated to be busy or congested, then certificates are omitted using the periodic omission strategy. This scheme improves the overall packet loss. That is when you combine both network packet loss and cryptographic packet loss together. should evaluate them individually, you realize that there wasn't a fair trade-off between these two. So a transmission power control certificate omission strategy was also proposed, which makes use of a combination of the NEPA-based certificate omission strategy and a distributed transmission power control algorithm. This scheme was able to reduce network packet loss and also it was able to reduce significantly network packet loss, and it was also able to reduce cryptographic packet loss, but it slightly outperformed the NEPA-based certificate omission strategy in reducing cryptographic packet loss. So the research gap we identified and we want to solve with our proposed scheme is that we noticed that all the above schemes do not maintain a steady and a minimized number of cryptographic packet loss and network packet loss, even as traffic congestion increases. That is, as the population of vehicles within the vehicular environment begins to increase, we realize that with these schemes, cryptographic packet loss and network packet loss begins to spike up. And this is what we want to solve by proposing a scheme that will be able to keep at a steady pace the number of cryptographic packet loss and network packet loss incurred even as traffic congestion increases. So with our proposed scheme, we will first take a look at the congestion detection mechanism of the scheme. And with this, we employ the use of a decentralized congestion control mechanism as proposed by ETSI. So this scheme allows vehicles to estimate their communication channel load using the formula n times beacon rate times the message length, where estimated CL is the estimated channel load, n is the number of neighbors, beacon rate is the beacon sent per second, and m length is the beacon size. And after a vehicle has estimated its channel load, the vehicle can then classify the channel into either a relaxed, active, or a restrictive state. And this is a diagrammatical representation of how the congestion detection mechanism is expected to function. Now, after a vehicle has detected congestion or has performed the congestion detection, then now our congestion control mechanism also comes into play. And with this mechanism, we first make use of a certificate omission strategy. So if a vehicle should estimate its channel load and observe that the channel load is below 40%, at this threshold, we assume that the channel is still free. So in this situation, a no omission strategy is performed where vehicles attach a certificate to every beacon is sent out. And with this, we purport at reducing the level of cryptographic packet loss that are incurred. But if the vehicle estimates the channel load and the channel is estimated to be above 40%, that is, the channel is getting congested or congested, then we immediately switch to a neighbor-based certificate omission strategy, where it is purported as decreasing both the number of network packet loss and cryptographic packet loss incurred. Certificate omission strategy alone will not be enough to properly and efficiently manage the communication channel. We propose to supplement it with a transmission power control strategy that is based on fuzzy logic, which will help the vehicles to intelligently select the right transmission power with which they can transmit their message based on the estimated channel load. This will also help to reduce the level of network packet loss and cryptographic packet loss incurred. So, looking at a diagrammatical representation of how our scheme works, we first begin with how the certificate omission strategy will work, considering this is a vehicle and the circle around it is its communication range. So, if a vehicle should estimate periodically its channel load and finds out that the channel load is below 40%, at this threshold we are assuming that the channel is less busy. So, with this, the vehicle will perform a no omission strategy where it attaches its certificates to every beacon it transmits in order to reduce cryptographic packet loss. But in the situation where the vehicle estimates channel load and is above 40%, then the vehicle will immediately switch to a neighbor-based certificate omission strategy where it omits certificates from its beacon until it identifies a new vehicle within its communication range. Then it will go ahead and update its neighboring table, attach a certificate to the next beacon it is sending out, with the expectation that the new vehicle within communication range will cache this certificate in memory, and in so doing, it can omit it in subsequent communications. After we've performed this certificate omission, as we mentioned, this alone will not be enough to properly manage channel congestion. So we designed a transmission power control algorithm which is based on fuzzy logic. And here we modeled a single input, single output fuzzy logic, and we'll take a look at the stages involved in modeling this single input, single output fuzzy logic. So we defined our parameters, and the input parameter was chosen to be the channel load, and with the corresponding linguistic variable being relaxed, active, and restrictive. So if the channel load is between 0 to 15, it is in the relaxed state, 15 to 40 is in the active, and 40 to 100 is in the restrictive state. If and our output parameter was selected to be transmission power with the linguistic variable low, medium, and high. And if transmission power is between 0 to 15 milliwatts, it is low. If between 5 to 15 is medium, and between 15 to 20 is high. And after this, we constructed our rubies, where we constructed our membership function, where the input membership function was modeled as we see here, with the x-axis being the channel load and the y-axis being the membership degree. And with our output membership function, we also model it with the x-axis being the transmission power and the y-axis being the membership degree. And after this, we then went ahead to construct our rubies, where we made use of 3 rules. The first rule being that if the channel load is estimated to be relaxed, then the vehicle should transmit with a high transmission power. If channel load is active, it should transmit with a medium, and if it is restrictive, it should transmit with a low. Then after this, we perform falsification, where we convert the input values into fuzzy values using the triangular and the trapezoid method, as can be seen here. Then we go ahead and perform our inference engine, where we evaluate the rubies. And after evaluating the rubies, we then perform a diversification, where we convert our output value into a non-fuzzy value, and we will make use of the mean of maxima method. So we want to also take a pictorial view of how this transmission power adaptation based on fuzzy logic works. So assuming this is a vehicle with a number of vehicles within its communication range, we assume that at the initial communication, the vehicle is broadcasting at its highest transmission power, which will be 20 milliwatts in our scenario. So if a vehicle estimates the channel load to be something above 15%, let's say if the estimated channel load is like 41%, then in this situation, based on our linguistic input variables, it means that the channel is in the restrictive state. So the vehicle will classify the channels to be restrictive. And after it has done this, it will go ahead and generate a distress signal. And in this distress signal, the vehicle would piggyback into it the observed channel state, which in this situation is restrictive state, and also the number of vehicles within its communication range, which in this example is 1, 2, 3, 4 vehicles within the communication range. And then it will broadcast this distress signal to its neighboring vehicles to prompt them of the current channel state and the number of vehicles that are communicating and contributing to this channel state. So after it has done this, going through the procedure and the steps of fuzzy logic, then the vehicle would evaluate the rule base. Because the estimated channel load is seen to be in the restrictive state, meaning the vehicle will broadcast with a transmission power that it's within the low range, and this transmission power will directly then cause the vehicle to decrease its communication range, because transmission power has a direct impact on communication range. And when this happens, we see that some of the vehicles, these 2 outlying vehicles, then fall out of the communication range of the vehicle that estimated the channel load to be congested. And then based on this will also help relieve the channel load. Now, we want to take a look at how, if a neighboring vehicle also receives this distress signal, how it can also cooperatively respond to help relieve the channel load. So, assuming this is a neighboring vehicle, if it should receive this distress signal, it will then extract the data that was piggybacked into the distress signal, which was the channel state and also the number of neighboring vehicles. And with this information, it will estimate the channel load to confirm the message to confirm the distress signal it received. And after performing this confirmation, then the vehicle will also, going through the steps in fuzzy logic, will then tune its transmission power by intelligently selecting the right transmission power with which it will transmit. And with this situation, using fuzzy logic, we will notice that the vehicle would also correspondingly select a transmission power in the low range, which will also help it reduce its communication range, and as such help to relieve the distress on the communication channel and help to also reduce channel congestion. So when we look at our scheme, then the major contribution we can say is the reason why we propose this scheme is that our scheme is able to enable vehicles to dynamically and also intelligently select an appropriate transmission power based on the observed channel state. So, in performing our simulation, we first made use of Omnet++ as our network simulator, Sumo as our traffic simulator, and we simulated the in-lagging map, and also we generated from 100 to 400 vehicles to have a varying traffic scenario or congestion scenario, and we made use of VINs where we conform to the basic safety message format. We modified the application layer to implement our omission strategy and the MAC layer to implement our transmission power strategy, and we performed 10 simulation runs. We made use of two. For this presentation purpose, we'll take a look at two evaluation metrics, which first of which is the percentage of network packet loss that were incurred and the percentage of cryptographic packet loss that were incurred. And the baseline scheme with which we compared our scheme is the periodic omission of certificate scheme and the neighbor-based certificate omission scheme. So when we take a look at the percentage of network packet loss, following the color coding, the blue will represent the periodic omission strategy, the orange represents neighbor-based omission strategy, and the gray represents our strategy. So, and the x-axis are the population of vehicles, meaning 100 vehicles, 200, 300, and 400 vehicles, and the y-axis being the percentage of network packet loss incurred. So what we notice here is that with the periodic omission scheme, as the vehicles increase from 100 to 300 vehicles, the periodic omission scheme incurred an increment in the number of network packet loss incurred, and the increment difference was 33.95. This was the increment difference. And when we take a look at the neighbor-based certificate omission strategy, as the number of vehicles increased from 100 to 300, it incurred an increment of 26.64. But when we come to our scheme, even as the vehicle population increased from 100 to 300 vehicles, our scheme was able to incur a network packet loss increment of only 7.05. This means that, as we mentioned earlier, the currently existing schemes do not maintain a steady number of network packet loss as vehicle population increases. However, we were able to create a scheme that was able to minimize the number of network packet loss and also keep it at a steady pace. Now, we also want to take a look at the percentage of cryptographic packet loss incurred and also analyze how our scheme performed to the other schemes. When we look at the periodic omission scheme, as the vehicle population increased from 100 to 300, we notice that it increased by a difference of 1.56. Looking at the neighbor-based certificate omission scheme, it increased by a difference of 1.99, whereas our scheme only increased by a difference of 0.59. And this, as we mentioned, our scheme is able to minimize the number of incurred both cryptographic packet loss and network packet loss, and even still keep it at a steady and a minimized pace even as vehicle population continues to increase. So to conclude, the state of the art of certificate omission strategy is known to face the challenge of how to maintain a fair balance between cryptographic packet loss and network packet loss as traffic congestion increases. Recently, a transmission power control certificate omission strategy was proposed, yet it was unable to significantly outperform the neighbor-based strategy in reducing the number of cryptographic packet loss. As such, this work proposes an AI-based transmission power control certificate omission strategy, which adopted a hybrid certificate omission strategy supplemented with an intelligent transmission power control algorithm based on fuzzy logic. the simulation result, it shows that it is able to attain a steady and a minimized number of cryptographic packet loss and network packet loss, even as traffic conditions. These are the references.